is coming, we asked to wait them.
Yeah. You're going to say hi to yourself. Before.
Good morning, everybody. It's my great pleasure to introduce today Piotr Smolarkiewicz, with whom we were a long time ago colleagues in the same institute in Warsaw. He left a long time ago and he's now at MCAR. And he's very well known worldwide as, among other things, as an author of a numerical code called EULAG. And he's now applying that code to new research, in particular MHD. And today he's going to tell us about that.
Thank you very much, and thank you for giving me the opportunity to present this research, because I am atmospheric scientist and I am actually with the second program, and solar MHD is what I am doing. It's a part of my work, what I am doing kind on the side, because curiosity-driven research. So that EULAG appears right away in title to draw the attention to the fact that talk is really about how we are going to solve the equations and numerically. And even though there is this background of physics, of particular solar physics, it's more general than just this particular problem. The same ideas that I will show, they apply to different kind of equations. And the fact is, it's a living proof that the MHD code has been developed from this Eulerian Lagrangian code that originated as a research tool for studying atmospheric circulations. But then it grew up into a fairly general code that can cover a range of scales from like centimeters to problems in cloud physics to mesoscale environmental flow. You can see something like storm by Sierra Nevada, we've done those things, to global atmospheric circulations, and on the other hand, problems from the flows in a wind tunnel, like flow path model of Pentagon. I did the work like this. Then oceanic current in laboratory, in aquarium, real simulation of like a mesoscale oceanic problems, up to now solar convection with MHD. So this my work on solar convection started about 10 years ago. I was on sabbatical in Reading and I had a talk then about atmospheric code, and Julian Elliott, who was a graduate from here, from Cambridge in astrophysics, he attended my talk and he encouraged me to apply it to solar convection. We worked together, we wrote paper. And then Julian went to do different things, and I got together with Paul Charbonneau, who is now in University of Montreal, and over years, we developed this MHD code. Took about 10 years until we got, in 2010, pretty amazing result. And I show you result up front, and then I will talk about how we got it. So this is the display of the radial component of the velocity from the simulation, or think vertical. And what it shows is that it shows those features of, those are convective plumes. Entire animation is on a scale of few solar days. So this is short scale. Solar day is 30 Earth days. And it shows like a convective plumes and the super rotation of solar equatorial zone. This is what sun does. It has a faster rotation on the equator. The second picture shows the radial component of the magnetic field. And one thing to note is that you can see that magnetic field is actually carried with the flow. So it's like in solar convection zone, it is frozen to the flow. Now, the most important thing, the most amazing thing is that on a scale of hundreds of solar days or solar years, and this is the next picture, and this is display of the magnetic field, zonal magnetic field, there is a large-scale oscillation. This simulation reproduces this large-scale oscillation. You will see that over the years, it changes polarity from and the cycle is on the upper panel. It shows the vertical cross section in the equatorial zone, and so this is this is horizontal near the bottom of the convection zone. It shows those like regular cycles. The movie only shows like maybe 1.5 period or something like this, but there is many more. And then this is vertical cross section. So this was a very amazing result before. There were no result like this before, and probably there is still no result like this, but people are catching up. Now those things, I will not talk about physics much here, simply because I am not an astrophysicist. So, but those things are, there is already several papers in the literature discussing those cycles and the physical aspects, and also this list gives me opportunity to present my colleagues, Mihai Ghizaru, who was patient enough to run those simulations, who actually found those cycles, Paul Charbonneau, whom I mentioned, and this was this first paper that shows those results. Then there is another paper in Astrophysical Journal that actually took those results from simulation and analyzed them and found out that those numerical calculations, those numerical data, they actually behave like one of those mean field theories results, like alpha dynamo. It's called alpha dynamo. It's like taking in fluid dynamics some results, averaging them appropriately, taking perturbations with respect averages, averaging them back, and showing that your simulation, direct simulation, actually behaves like Reynolds average Navier-Stokes equation. So this is in this spirit. And then there is a new paper already in Press in Solar Physics that is going in depth more to the properties of oscillation. But what I am going to talk about is the work that is now submitted to JCP. It's in review, and it's about the details of how we do this. So here, what I am showing you are equations, how typically they are presented in astrophysical literature. So if you are not familiar with MHD, but say you are familiar with fluid dynamics, you can recognize quickly that what those equations are. This is just like momentum equations, and has a total derivative. There is a Coriolis force. This all makes like a material derivative. There is a pressure gradient, gravity. Then there is a divergence of viscous stress, and this is just zero. This is hydrostatic balance of the anelastic reference state. Those are anelastic equations, which means that the mass continuity has no time dependency of the density. There are no time-dependent density fluctuations. And this addition, which goes beyond fluid equation, is that there is a magnetic field, B, that enters a momentum equation through the Lorentz force. This is Lorentz force. And the magnetic field is non-divergent, has no sources. And then it satisfies also mass continuity equation. And this is entropy heat equation, written actually in terms of entropy. And basically, this is it. So now, when you look at those equations, there is great amount of details on the right-hand side. And all those terms, like here it is the divergence of the stress, viscous stress, is written symbolically. But when you go to the entropy equation, then there are various terms that depend on different forms of viscosity. So this is actually physical term, radiation diffusion. This, in real world, would be molecular diffusion. In computational models or theories, the K is replaced with eddy viscosity and plays the role of the turbulent parameterization. Then there are those other terms also depend on viscosity, because this is like viscous heating, I believe, and this is related to magnetic resistivity. So those terms like that are physical, they are small. This is this and the volume heating. They are small compared to the terms that use subgrid scale parameterization in calculations. And now,
What are the bars on
bar?
Well, there's S and S bar.
Oh, okay. Anelastic equations are like derived from asymptotic expansions around some static reference state. And this reference state is described here as a bar. And it's not arbitrary. It has to satisfy certain properties of the equations conserve energy. It's actually a good question because I would forget to mention.
So the main point, I think, here is the critical point is that the induction equation, number 5, has no subgrid modeling as far as I can.
Well, depends. This is resistivity. So if one puts the real resistivity, then it's very small in real sun. But some people can, in numerical model, one can put whatever one wants. So it can be as.
Is it constant in space, or is it a function of something else?
No, here it is constant. Actually, we don't even use it. This is, I was saying, how equations are typically presented. But now coming from the experience from atmospheric modeling, we rewrite those equations in different way. Those are the same equations, they just have a different focus. They emphasize different things. So let's say that, let's refer to this form as a Maxwellian kind, because it has all those formulations that reminiscent of Maxwell equations. Whereas here we write them more like in a Newtonian form when there is an acceleration of the left-hand side and forces on the right-hand side. Now, why is it so? When you remember this first picture that I show you of the magnetic field, it is really like attached to the flow. And magnetic field on sun is relatively small. Those effects are small. And this is just an example from some control simulation that is in this JCP paper. There are 3D box with potential flow induced by flapping membranes. And there is a magnetic field embedded in it here. And this is all scaled to represent reality of solar convection zone. So when you squeeze the field, it squeezes, then it stretches when the walls go up, and then it comes back to this form. So I didn't plot the last one. You cannot distinguish the difference on the picture. There are some quantitative analysis shows that there is about a 1% departure. However, those effects are small, and increasing magnetic field by factor of 10 gives final solution somewhat deformed compared to initial condition, and only increasing it by a factor of 100 leads to completely qualitatively different solution. There is, when those two membranes approach, there is a burst of jets, magnetic jets, and becomes like a chaotic solution with some structure in it. So because of this, we emphasize this total derivative, which is really convection, and because we write the equation in this form, those, like a Lorentz force and induction force, they can be written differently. In this case, Lorentz force becomes like a convective operator, convective derivative operator, except that this is like a magnetic field convected with magnetism. I mean, this is not, of course, advection, but in terms of the form of the operator is concerned, it's the same. It could be V grad dot V. This is what's sitting in this thing. And then another, there is a term that is a gradient of B squared, but it's subsumed in pressure perturbation, because ultimately problem is controlled by the mass continuity and elliptic equation for pressure, so it doesn't matter what is the pressure. It depends on the explicit right-hand sides of the elliptic problem and boundary condition. And the result will be the same. Only when one wants to diagnose what the pressure actually is, later on one needs to subtract b squared from it, term proportional to. Now, we don't write our heat equation in terms of entropy, but we write it in terms of the potential temperature. Potential temperature was introduced by Helmholtz in 1888 to study atmospheric motions, and this is all discussed in the Bauer 1908 paper in Physical Review. Actually, this is an interesting paper because it discusses the relationship between entropy and potential temperature. For for ideal gases, entropy and potential temperatures are tantamount because just perturbation of entropy is constant specific heat at constant pressure times perturbation of the logarithm potential entropy. Why is it convenient to write it in this form? Because we are formulating an equation that we'll be solving for the same quantity that appears linearly in a buoyancy term. And because of this, we will be able to design effective implicit schemes for integrating those equations. Implicit not necessarily for stability, but for balance and accuracy. And now we de-emphasize viscous terms because physically we are not able to resolve in calculations those physically meaningful terms. And when it comes to those, how Max Gunzburger said, numerical facilitators, they can take very different form. So if one wants to put something here, one can imagine variety of possible forms of viscous terms. Now, those equations were in the intuitive Cartesian-like form. Ultimately, we have to solve them on manifolds and in different geometry than just Cartesian. Here I show you this. This is those flapping membranes that I mentioned before. Equations in this example that I show are solved on something like this, except that the magnetic field is embedded inside. Once you move to manifolds, then there is a increased level of complexity. So having those starting equations written in a simple, fairly symbolic form pays back. The model is formulated in a time-dependent curvilinear coordinates. Not exactly like general relativity. There are some simplifying assumptions, like that the time is the same in both system of coordinates in a computational space and physical space. So this is, and there is assumption that horizontal coordinates do not depend on a vertical one. So that the vertical columns stay vertical.
In the manifold you have in mind is the surface of the sphere.
Sphere is a simple example, but it could be different. You could have a surface that is a sphere that is very deformed.
In solar application.
Yeah. Mm-hmm. Yeah.
Spherical annulus.
Yeah. Annulus. This is spherical annulus.
Spherical shell.
Yes. Exactly. We'll get to it. Now, this immediately implies that this total derivative is just a standard composition of partial derivative and convective derivative, but convective derivative is a now velocity that is of in the transform system. And this symbol here does not mean any like a covariant derivative or nothing like this. It's just nabla. So all this derivative can be written in terms of partial derivative in time and convective derivative, except that the velocity is something that comes from the transformation. Why is it important? Because those nablas can be identified with basic finite basic differential operators in the numerical code. Those are your psi I plus 1 minus psi I minus 1 divided by 2 delta x, and so on. So this is like a simple way of thinking about those transformations that allows to extend Cartesian codes to complex problems with complex geometry. Then equations are still formulated for the physical variable of physical space. This is not what theoretical physicists would do, because in theoretical physics, equations are written in invariant form, and we'll use like those contravariant velocity of the space they are formulated in. However, here, this is invention that comes from aerospace engineering. It's called strong conservation formulation, when the dependent variables are retained from the physical space, and only velocities that transport dependent variables are transformed. And why it is important? Because if one works in this like a crazy system of coordinates like this, one does not want to have a conservation loss for the velocities of the systems. They are not necessarily physically meaningful. Whereas those U's, U, V, W's component, they are measurable Cartesian like velocity. You have a question? No?
Sometimes sometimes invariant formulation is critical if you really care about conservation.
Yeah, this is, and also this is the this is not something one has to do. It's an observer who decides what is physical velocity. Good example is, for instance, like if I solve the fluid problem in polar coordinates for some reason, I may decide that my radial and angular velocities are my physical velocities that I want to formulate equations for. But on the other hand, I can formulate equations for still Cartesian components U and V, but transfer them and the whole equation expressed in the polar coordinates. And this is the virtue of this approach. The key virtue is numerical, because if I retain original variables of the physical space, I add no Christoffel terms due to the coordinate transformation, because this is where the Christoffel terms are coming from, that the velocities get redefined. And Christoffel terms are nonlinear, so if one works like with any two-time level scheme, like forward in time, those things are difficult to integrate. So we want to minimize this type of problems right up front. One consequence of working in time-dependent coordinates is that there is yet another form of velocity that appears. We refer to it as a solenoidal velocity, and this is the one that satisfies mass continuity equation. Because I could write the same inelastic mass continuity equation as a d rho star dt plus this nabla dot rho star us. Rho star is a product of an elastic density times Jacobian of coordinate transformation this. So even though the system starting was like mathematically incompressible, when you transform to time-dependent coordinate, it looks like compressible. But it can be avoided by defining this solenoidal velocity related to this used to the contravariant through the velocity of the grid. There is nothing like this for magnetic field, because magnetic field, the solenoidality of magnetic field does not involve those it's not like a continuity equation. This is related to the fact that this is velocity. Those things, there are very nice direct transformation between solenoidal velocity and physical. And those matrices, they come from the geometry. So this is like when one solves for U, one can immediately get by solenoidal velocity, and B get the solenoidal field, which is the one for B. This is the same like contravariant, that is one involved in a transport. So all this, the writing goes this way. It's a continuous flipping between different for velocities by matrix multiplication. now we simplify it even further. So now we go to case.
G view is not zero and it's compressible. So if you make a small mistake, a small error in D view, that doesn't make much difference. But can you ensure that div B is zero throughout?
Yeah, but there is nothing you can ensure exactly. At best, you can do this to the machine precision.
Yes.
But I will get to it. Actually, this is all very thoroughly discussed in this JCP paper, because people tend to believe that divergence cleaning, this is one of the, I'm getting ahead of the story. We'll get to it. Yes, I address this thing. So now, let's move to the case that we are actually solving. We did use this previous form of the equations to do this flapping thing that was involving time-dependent coordinates, but for the solar cycles, we just work in a spherical system of coordinates. This is meteorological formulation known from weather and climate, because the equations are actually formulated in a surface-based system of the coordinates. Like when you drive your car in London, you work in a local system of coordinates. Your velocity is, for instance, from west to east, x component, another south-north, and yet another up. So it's called, in some texts, an holonomic system of coordinates. I refer to it as a geospherical framework. I've heard it from Daryl Holm, but really it comes from Aristotle, I think, or it's a tribute to Aristotle. So the relations are global, means that the coordinate x is related to radius and the cosinus of the latitude and the increment in longitude. Now, and so on. This is standard. It's very nicely described and illustrated in Dutton's textbook it's called Ceaseless Wind. Those coefficients come out straightforward. Gamma is a ratio of the radius, actual radius, to the radius at the base of the spherical shell. So this is what it is, and so it accounts for radial extension. The nice aspect of this that there is no solenoidal velocity and contravariant velocity. There are only those contravariant and physical, so the transformation between the two is simple, and the mass continuity looks like this. And here, so this is just natural extension. Here we make one physical modeling assumption. So in those equations, the very first that I show and that you asked the question about, what are bars, anelastic equations are standardly written as perturbation around the reference state. And the reference state is something like carved in a stone. Otherwise, equations do not conserve energy. However, there is another trick one can do, is to assume that I know some arbitrary balanced state, which is a particular solution of the governing system of the equation. And this can be anything that satisfies those governing equations, and it only depends on how much we know. So what we do here, we are assuming that we have an ambient state that is hydrostatically balanced, but it doesn't have to be like a constant stratification or isentropic, nothing like this. And it satisfies, so this is hydrostatic balance, and the state is referred to as E, whereas those zeros here, this is what the bar were in the notation of the first slide. So those are the reference pressure and the reference density that can, in this particular case, those bar is the reference state is isentropic. So here is the anelastic, this is the hydrostatic balance for the ambient state, and the potential temperature will be assumed, or is assumed in calculation as being stable in tachocline and weakly unstable in solar convection zone. So now we subtract those things from the basic generic anelastic equation, and these primes now refer to the perturbations with respect to this ambient state. Here, there would be this viscous term, heat flux, in in the potential temperature equation, and we are assuming, actually you can derive it by doing averaging over a long time of the equations, assuming static state, and there will be something like a Reynolds heat flux that comes from this, because it's average over a spherical surface at every radius and over a long time. It's like a mean sun. Sun does not change much did not change much over the history of civilization, so one can assume that this observed state is actually fairly stable. So there is this, when you do this, there is an uncomputable unknown, like a Reynolds heat flux, and for this we just assume the rest is with respect to this, it's like, for instance, radiation diffusion with respect to ambient potential temperature. Then for this thing is parameterized as a attenuation. This is called Newtonian cooling, that this term, introduced arbitrary, does not allow the system to deviate too much from the balanced state. And this alpha is selected as on a scale of 10 to 8 seconds, so it's large. Oops. Okay, so this is about equations. Now we come to how we solve them. So when it comes to solution, it is actually simple. We don't look at the details of the right-hand sides, at the details of those equations. We view them as a Eulerian conservation laws, and the previous form of the equation is readily converted to this by multiplying equations by density and mass continuity by dependent variables and combining them from evolutionary form to the conservation form. This is elementary. So now those equations can be written for all those variables, three components of velocity, potential temperature fluctuation, and magnetic field, can be written as a vector conservation law, and those R's denote associated right-hand sides. We do the trick. This is the thing that while solving those equations, we switch from the convective derivative type of operator, here in both induction force and Lorentz force, to conservation form. And this is nice. This has a numerical implications. And it's easy now recognize in actually coordinate dependent form, it's easy to recognize who moves whom, because those are B stars and V stars that advect fields. Those are those velocities that advect. So U star advects U, or B star advects B, moves, advect, I shouldn't say advect for the magnetic equation. And now the algorithm for solving this comes from, well, it was built up over years. It's a second order in time method. Forward in time means that there are two principal time levels, old and new. There are no like Runge-Kata, strip time levels or leapfrogs. It's just from n to n plus 1. And if I need something in between, then I have to have some estimation of the value at intermediate time level using the governing equations. This is in the spirit of those, like in final element Taylor-Galerkin algorithms, or one-step Lax-Vandroff scheme and so on, but it's taking to different levels. And this operator A is actually advection in a conservative form. So this does this thing, and this is a very particular advection. It's based on those multidimensional positive definite advection transport algorithm that gives you solutions that are sign preserving, monotone, and bounded with square, and so on. Nice properties, and this is important. We get back to this. So all this, this algorithm can be effectively written that my new solution is some explicit part plus new force, half of the new force, because the assumption is that the force is represented as a Crank-Nicolson integral. It's implicit. And now, of course, I don't know right-hand side at the time when I want to get psi. So the problem, this is where we got to those elliptic equations. And so the standard way of doing this is to identify in those right-hand side the forces that are linear and non-linear. So it's not just R. Now we identify linear operator asking on psi, which will be like Coriolis, for instance, or this part that appears in V dot grad theta E, convective derivative of ambient state in equation for the potential temperature perturbations. Then non-linear part, and those would be like Lorentz force, induction force, or those Christoffel terms, which are metric forces that appear symbolically in a momentum equation by m of velocities or m of b's and so on. And there is a pressure gradient term. In momentum equations, this is just normal pressure. This is related to physical pressure that is the homogeneous part of the stress. In entropy or potential temperature equation, there is nothing like this. We don't add, there is no gradient of extra potential. In magnetic equations, in induction equation, we introduce bogus pressure like, this is P star. We add the gradient of P star. Now, why do we do this? It's in anticipation that we have to assure that div B is equal to 0. And this will facilitate for us formulation of elliptic equation. Now, the only reason why B loses its divergence are truncation errors. And the entire scheme is of the second order. Therefore, that those are this phi star is at the level of higher order truncation errors. So we play games on the higher order truncation errors to formulate elliptic problem and to assure non-divergence. The rest is conceptually easy, because what we do is that we identify linear part, bring it to the right-hand side, and invert, which means this is work on a paper. You just write those equations and derive those coefficients. So we have that the solution is the solution is the inverse of some linear operator acting on a modified explicit part. This comes out from solving on a paper those equations and assuming. Oh, I've forgotten to say something important. So in order to solve this, and we have this nonlinear part, we impose outer iteration. And that means that the nonlinear terms, they are lag in time, or in iteration, not in time. We are having outer iteration, they are lag in iteration, and therefore they contribute to the right-hand side, and this leads to the modification of this right-hand side. So the entire problem is basically solve. This is the closed form solution for the dependent variable at new time level, and now we apply those constraints of divergence to find those potentials and to complete the solution. This is idea. In practice, it gets more complicated how it is done, because the idea is realized in a way that we update different parts of the forces immediately when we get a new update of other variable. For example, when we come to the hydrodynamic part first, we actually use the non-conservative form of the induction equation and solve it implicitly to get the prediction of the magnetic field to use in the Lorentz force and in those Christoffel terms. And then the rest is already like a full implicit problem. No, this is also lagged in time. But this gives us, together with this formulation of potential temperature, which is implicit, and imposing this constraint, give us the new velocity. And then we again, having new velocity, we again make a prediction for magnetic field, that we then use in a induction equation. So the update is immediate. It's in a philosophy of Gauss-Seidel, but it works. And typically 2 outer iterations suffice for practically converged solution with the first order solution as a predictor, starting as a first guess. So now we go to basically to the end of it. So the model setups were that we solve on this spherical shell that goes from 0.62 to 0.96 of solar radius, and it spans 3.5 density scale heights. There is a solar rotation. Theta E, as I mentioned in here, is stable from up to 0.7 of from 0.62 to 0.7 of the shell, and then unstable aloft. And this attenuation coefficients that assures the balance in the entropy equation or the potential temperature is 2 times 10 to minus 8 over second. Alpha is like 1 over time scale. So then this is like 20 solar days. And the simulations are done on fairly modest grid, 47 by 64 by 128. 6428 is in a horizontal, 47 level is in radial. They are by nowadays standard low resolution calculations, but take into account that we are doing about 10 million time steps. So this is very long calculation. And then we come to the point that why we didn't have de-emphasize those viscosities. So except for the entropy equation, potential temperature, I should keep saying entropy, this is really the same thing. We rely on a so-called implicit large eddy simulation. This is how it is referred in literature. There is a book, Implicit Large Eddy Simulation, published several years ago from Cambridge University Press, that has articles, chapters throughout the computational physics showing application of the implicit large eddy simulation in different areas. And implicit large eddy simulation goes back to J. Boris FCT schemes, that it was found later and described in literature that some of those schemes they have included subgrid scale parametrization. That not all truncation error terms are really errors; they are just truncation terms, and they have properties of the same like explicit subgrid scale parametrization. Here is just an example how it works. Here is the resolution, the picture of this cross section through vertical velocities, radial velocities. At the resolution that I just mentioned, 64 by 28, and here at twice larger. We increase the resolution, then the solution actually develops more and more structure, and it's nice and regular down to the grid scale. This is evidence from climate studies, has nothing to do with this, comparing different models, and shows that red is EULAG, that for instance this is Eulerian climate model, spectral, this is finite volume, this is this code, EULAG, and it has a nice behavior of spectral for even in a tail, and doesn't show the same dissipation like, for instance, other finite volume schemes. Here is yet another illustration. This is the result picture of the radial velocity taken from this from ASH. This first slide that I show with equations was from the group that uses anelastic spherical harmonic code that goes back to derives from codes that originated by Gary Glatzmeyer. And this is at much higher resolution than this one. And what the difference is this richness of structures that compare to this other code. I'm not saying it's bad or good, this is the difference. Now coming back to cycle, and I am basically almost done. So this is what colleagues did, this analysis with respect to how the numerical data, what they tell us. So when you take actual solution field, subtract from them some average, or zonal average. Here theta is, in this language, theta is a latitude. So, and this is also some temporal. So it's a smooth field which is zonally average. So when you formulate those perturbations, then the induction equation can be written in this form, and this is there is this like electromotive force, if I remember, that comes from the subgrid scale motion contribution. But because the data exists, it can be actually calculated. And what you have here, this is the average this like a subgrid scale term that comes from the fluctuation, and this is the average zonally, because this is time and this is latitude, and this is average zonally this mean term. And when you look at them, they are quite symmetric, quite similar, but shifted in phase. So what really acts in the right-hand side of the induction equation is a sum of those two. And it's a much smaller delicate balance. This one that drives those oscillations, it has those oscillations which are on a much smaller magnitude than either of the two terms. Therefore, the conclusion is that actually the result are sensitive to how viscosity is introduced to the model because of this. Depending any deviation or anything in a viscosity is numerical or explicit can destroy this delicate balance. So actually it shows that it's better to have as little viscosity as possible. And this is what implicit eddy simulation does. So now coming to remarks. So there are differences between our simulations and a real cycle observed on the sun. That life is not that wonderful. Like for instance, our period is too long. But there is lots of solar-like behaviors and similarities to the real sun. So no matter, regardless of those departures, the fact is that those regular cycles in a global MHD simulation of solar convection, actually they are available now, they exist. And EULAG-MHD offers an outstanding virtual MHD laboratory allowing to address quantitatively a number of physical questions about the relation of the magnetic field and the flow and etc., etc. And that are, so they can only be speculated based upon simplified model formulations. There is much to be learned. For example, those calculations suggest that entire magnetic variability involves less than 10% of solar luminosity. And so this is like a delicate product of the entire system. And there is an interesting connection to to the physics of other, I would put it called dissipative structures. In Earth atmosphere, there are similar oscillations, similar kind of behaviors, like for instance, quasi-biannual oscillation, and this is that every 21 months, stratospheric mean wind changes direction, stratospheric mean wind over equatorial zone changes direction about every 25 months. And then there's also this Madden-Julian oscillation that the blob of the huge blob like gyre moves from Africa toward the Pacific, producing severe weather, convection, and so on, and this type of behavior very regularly. Numerics-wise, what we've learned, something very useful, is actually that the work of elliptic solvers is adaptive. We use those variational solvers that are iterative, and because we do those divergence cleanings at different occasions, when we solve main equation, but also when we calculate those like transportive velocities of magnetic fields that enter the induction force and Lorentz force. Those are actually just those B stars. Then we also do the optional divergence cleaning. So per 2 iterations, outer iterations, we have we solve 9 elliptic solvers. It sounds scary. And if one would use direct solvers, this would be unaffordable, right? Because every pass of direct solver costs the same, doesn't matter how accurate or inaccurate is solution. With those variational solvers, we use generalized conjugate residual precondition. One can impose accuracy threshold value, which is related to physics. And then when the solver knows that the threshold value is reached, that the required accuracy is reached, it exits. And the thing is that then it turns out that only 2 main solvers, one for the hydrodynamic part, one for the magnetic part, that they really do the work. And those rest, they just do very little work compared to those main solvers. And if one does not distribute them, but puts everything, does not do optional divergence cleaning, just only use those 2 main solvers, then those 2 main solvers make more work. So this creates opportunity to actually impose different accuracy constraints on an entire solution, place those efforts in different places at the same cost. And this is all. Thank you very much.
Questions? Comments? Yeah, for those who might have missed a detail or two, my observation is in general here that this is a very serious application of differential geometry for the simple-minded, those who don't do relativity and stuff like that. But atmospheric physics is where simple-minded differential geometry becomes very important because they often work in strange time-dependent coordinates like pressure surfaces and that sort of thing. But my fundamental question to all this is that I find it extremely surprising that the difference in numerics can make such a big difference, while if you have 47 levels in the radial direction, that you miss such a huge amount of physics there anyway. Should nevertheless the small difference in numerics between different codes can they make such a large impact on the result?
Those are not such a small differences in numerics. There are some aspects which are fundamentally different, like conservation, how conservation is enforced, for what particular dependent variables we solve, what schemes are we using. Those are not small differences, and you can take something very, very standard, like a pendulum. There is a famous short note in JCP by Miller. It's called Horror Story About Integration Methods. You can type it on Google and it shows. And he goes through like a simple pendulum and show what you can get with different type of methods. And actually those schemes, they are designed insofar as the ODEs that underline those conservation laws that we solve, they are designed in a spirit of symplectic methods. They are not exactly symplectic, but if you take special cases when, for instance, advection can be neglected and throw away some of those nonlinear forces, this is Crank-Nicholson. So those pendulums are fairly regular, have those regular behaviors. Those are big differences. And of course, lots of physics is missing, but we are not solving entire physics. We address some aspect of it. Like we don't have here those hot dark spots and so on, because there is not enough resolution.
Solar cycle is obviously something very subtle. It's a subtle, sensitive effect. If you
But this is not the first application that showed this. Like we did the work my colleagues and I on QBO and MGO too.
what is the period of the cycle?
The real one is what?
The real one,
11 years, right?
half cycle is
Yeah, and this one is twice longer. About.
twice longer.
Yeah.
Well, that's not too bad. It's not an order of magnitude.
No. And actually, we had very similar experience with QBO. There is it's beautiful laboratory experiment that goes to Plum McEwen. It's in a annulus filled with saline solution that gives constant stratification. There are pumps working regularly, which in a perfect linear world, it would just produce interference pattern of gravity waves. But then, because of minor perturbations, there is a spontaneous break of symmetry and the currents form. And once they form, the clock forms, and there is this mean current that moves up and down and changes direction. I have it here in the movie. And we simulated this thing. It was PhD of Neil Swede from Reading. And we had the same thing, that our period was the most difficult to control. And actually it came out to like a detailed observation of the movie. It turned out that one membrane was not exactly like others. And accounting for it improved greatly the prediction of the cycle or reproducibility of the cycle. So that cycle seems to be very sensitive on details. But in nature, somehow, it's not.
Well, the people here would certainly like to see the three-dimensional form of the magnetic field inside. You're only showing the
Oh, this is there are those physical papers that they discuss this thing. So my job is to make sure that equations are solved properly. I just solve equations.
Okay, thank you very much.